today in lecture 20 we will be continuing still our quest or means discussion about queuing theory, but in the queuing theory a specific topic called Little's formula, probably Little's theorem, that is something we will be discussing. So, this is we will discuss in due course what that means, but before that probably we will still this memorylessness process that we have discussed in the last class. We will continue on that little bit, some more property of Poisson and exponential and some more relationship with the queuing theory. So, this is what we will be doing. So, let us see what we have been so far doing is we derived the exponential distribution. We have also told how it is related to Poisson distribution. We have told that service and arrival process of a queuing will be actually dependent on this particular distribution, probably at least for the analysis of our trunk switch or analysis for our voice network or TDM switch network. So, that is something we have discussed. We have seen that there are practical evidence also that these things follows the similar kind of distribution. So, that all done. We have also derived some property of memorylessness of the exponential distribution. So, these things we have already done. Now, let us give some theorem. Of course, this is not the full course of queuing theory. So, that is why all theorems we will only be proving, but let us now give some theorem associated with Poisson or exponential distribution, which will be very useful in our derivation of later formulas. Okay. So, the first one is called Poisson merging. The second one is Poisson splitting, and the third one is minimum of multiple independent exponential distribution. Okay. So, what do we mean by Poisson merging? So, Poisson merging means it is like this. Suppose let us say multiple streams of independent Poisson arrivals are happening. So, it is two streams of Poisson arrivals are happening, each have a timeline, and in time they are doing arrivals like this. Okay. So, it is of course, the associated distribution is Poisson, and there is independently another timeline is there. So, there are also some Poisson arrivals are happening, and these two are independent to each other. So, when this arrival happens, that does not influence this one and vice versa. Okay. And like that I can actually take multiple streams. So, not only restricted to 2, I can actually take n number of streams, n can be any integer. Okay. If I take that and then I merge these two and construct a new process, that means each arrival whatever timestamp I have given, I will be taking one arrival. Then if in between there is arrival from here, that also I will be considering. So, I will just actually merge these two things and construct a new one. What will be happening to this one? Can we comment on this? Okay. It turns out, it can be proven very easily that this also remains to be Poisson independent of all the input that is feeding to this one. So, this is Poisson with the strength, suppose this was having a strength of lambda 1. So, that means lambda 1 was the arrival rate, this was having lambda 2 and so on lambda n. So, this will have a strength of course, the strength will be all added. So, it will be lambda 1 plus lambda 2 up to lambda n. So, this is a simple theorem of Poisson merging, that if two independent Poisson process or multiple independent Poisson process are merged to generate one process, that arrival process also will look like, means it will be a Poisson process which will be independent of all the inputs, and the strength or the average rate of arrival will become the addition of all the input ingredients or input Poisson flows. So, this is the Poisson merge process. What is Poisson splitting? So, like merging, now I will be splitting. So, suppose I have a Poisson source which is coming over here to a scheduler. Okay. So, scheduler is where I or somebody is sitting, and what they are doing. So, let us say I have this Poisson arrivals which are happening in time. Now, this scheduler, it picks every arrival at that time whenever it is happening. With that, it will be actually generating two flows, and how he constructs these two flows? He actually puts a probability. maybe he toss a coin and see what is the this one. If it is means it's a unbiased coin, sorry, it's a biased coin. So, it can have a head probability of, let us say 0.3 and tail probability 0.7, something like this. And from this means biased coin tossing, if he sees head is coming, he will put things over here in the first stream, and if he sees its tail, he will put in the second stream. Like this, he can also construct multiple this one. So, then coin tossing, maybe he has to do multiple coin tossing to generate multiple events, or he has to roll a die or some other things he will have to do. Associated means random experiment he will have to do, so that he can actually stream out the probabilities. And with those probabilities, so let us say with P1 probability he puts it over here, and 1 minus P1 probability he puts it over here. So, it has to be done with probability. You cannot just say, okay, the first one I put over here, second one I put it over here. So, those kind of things logic you cannot do. It has to be a random things. So, when you are splitting them, you are splitting them randomly. So, with that what will be happening? Two streams will be generated, and exactly whoever will be present over here, that will not be present over here. The next one might be present over here, next one also might be present, depending on the probability. Next, this one might be present, this one might be present over here. So, like this it will be splitted. Once they are splitted, now these two we can again comment, again it can be proven that they are also Poisson, independent of each other and independent from the input. And what is the associated means rate? The rate will be probability multiplied by this lambda, if it is P1, and 1 minus P1 multiplied by lambda. So, again these two are Poisson arrival, independent of each other, and they have a strength which is derived from the input strength and the associated probabilities. Okay. So, this is called Poisson merging process. That means, a Poisson's this one with probability, if you means branch them out, they still remain Poisson and they are independent. If two Poisson process you merge them, they still remain Poisson and the strength is addition of them. Okay. So, these two things we have seen already. Now, the next very important thing. So, now the exponential. So, let us say I have multiple exponential distribution, and from there I draw values. So, this xi's are taken from I for all I belonging to some set n, where n is having n number of indexed this one. So, each one of them is representing actually a Poisson data taken from exponential distribution. So, this will probably get at a particular instant x 1, this will get x n, and similarly the ith one will get x I. So, if I now for all these I do a minima over all I, and whatever that I note it as a new random variable. So, basically multiple exponential I take with different kind of rate probably. So, they might have, this might have rate mu 1, this might have rate mu 2 and so on, okay, mu n. I can take them, I can take a minima of all those things. What will happen to this x now? It turns out, again it can be proven, that this x is also exponentially distributed. What is the associated strength or the rate? That will be addition of all these rate. So, mu 1 plus mu 2 that should be the mu, and it is exponentially distributed. So, minima of exponential is also exponential, and they are all distributed, means this is also distributed with the addition of all the individual strength. That is what happens. Okay. So, with this we conclude to our special property of Poisson or related exponential distribution. So, we know now that if we merge Poisson process, what will happen? If we split Poisson process with a probabilistic manner, what will happen? And if we take minima of Poisson exponential, then what happens? Okay. You will see that all these things have application. Okay. So, now let us try to go little forward, and let us try to do the same experiment that we have been doing. So, in the queuing. So, I have a queue, I have a server, and then let us say this is Cn minus 1, maybe nobody was there, so he started serving. This is exponentially distributed with some, let us say xn minus 1, in between some arrival has happened, and then he waits, he joins over here. So, this is Cn, this is Cn, he starts getting service. So, this might be n, in between another arrival has happened, then he waits for this amount of time, he waits for this amount of time also his service, and then at this point he goes to the service, and this is, let us say x n plus 1, this is C n plus 1, this is also C n plus 1. Okay. So, this is how the timeline progresses, as we have already demonstrated. Okay. Now, as you can see, there are multiple events which are happening. So, if we just means from the outside, from outside of the system. So, basically our system is something like this. We have a queue followed by a server. So, this is the server, this is the queue, and this is the whole system. Okay. So, this is probably two doors I am just constructing. So, through this arrival happens and through this departure happens. Okay. Now, if I just from the outside I put an observer. So, what he will see internally, whatever is happening, he is not bothered about that. That somebody joins in the queue, he moves up in the queue, he joins the server, so all those things he is not interested, this observer is not interested about those things. So, for him events are some arrival is happening, some departure is happening. Okay. So, let us try to characterize these events, this sequence of events and what happens to those events. Okay. Let us try to see. So, if I just summarize this whole thing from the perspective of arrival and departure, I will put arrival in the bottom half and departure in the top half. So, this is one arrival. So, let us call that as C n minus 1. When that is departing, this is when C n minus 1 is departing. So, that is happening over here. So, this is the departure of C n minus 1. So, this I can call as D departure and this is the arrival. Okay. In between C n, that arrival has happened over here. In between another arrival has happened. So, this is C n plus 1. Then next departure, this has happened over here. Another departure, this has happened over here. Let us say I continue like this, no arrival has happened and one arrival happens over here. Then that immediately, because the queue is now free, everybody that has arrived they have departed. So, it is free. So, he immediately goes and joins over here, he will start his service. So, this is probably this is C n plus 2 and that is where same C n plus 2 will be going and this is where the departure happens. Okay. Just to demonstrate. Now, the next arrival, so basically nothing happens over here. So, this is where another arrival happens. And then after some times probably the departure. Okay. Now, let us try to see this inter events. We are interested in the distribution of these inter events. Okay. So, how they are distributed, can we now comment on these things? Okay. So, inter event distribution, if you now try to see this one, what is this? This is between two arrivals, that is exponentially distributed. So, this whatever this factor might be, that is exponentially distributed, that means that is memorylessness, that has memorylessness property. What about this? This is also between two arrival. So, it is again exponential. What about this one? This is one arrival and one departure. Now, what can I say about this one, this particular part? can I say anything from whatever discussion so far we have made? Let's try to understand this particular part and concentrate on this part. Probably this is the most important part of our journey of queuing theory with exponential or Poisson arrival and service. Okay. So, let us try to understand what is this. So, first thing is, this is where the last arrival has happened, okay, and next arrival will be happening over here, that is exponentially distributed with strength lambda. What is this? This is when, this is about a service that has begun over here. So, this was x n minus 1 and this is the first time that is departing. So, this is again exponentially distributed, right. So, this x n minus 1 is exponentially distributed from this point to this point. So, that is exponentially distributed, this is also exponentially distributed. So, basically this is actually part of two exponential distribution, this one and this one, but both, for both the cases it is partial. So, now the partial property comes, that memorylessness property. So, if this is exponential, what about from this point to the rest of the things? We have already discussed in the last class that the residual part remains exponential for exponential distribution. Of course, we have not derived this, we have just done the memorylessness property, from there we could understand that. Okay. But exactly why that happens, that requires we need to do renewal theorem and then we need to derive the residual distribution, but that will come to exponential with the same parameter as whatever parameter it has, the original one has. So, this is something we have demonstrated. So, this will still have distribution with mu. So, this rest of the portion. Okay. What about over here? Over here also, so when this is happening, so basically as you can see, this particular point can happen, either there can be one arrival or there can be one departure. So, basically all the time what is happening, so from a particular time instance, suppose from here, if you even try to see this guy, what is happening, one service is going on. From here that service time is exponentially distributed, that has not finished, in future somewhere that will be finished. From here one inter-arrival has started, which is also exponentially distributed with parameter lambda. So, among these two there is a competition, whichever finishes first, that will declare an event. If the arrival happens first, that means he is still in service, one arrival happens, then that will be the first one, like this event has occurred. From here to here one service is going on, he is still in service, another arrival has occurred. Okay. But from here to here what has happened? So, basically one service was going on, that service has finished before the next arrival has happened. So, basically two exponential which are having now competition, and whoever is the minima among them, now that principle of minima of exponential distribution comes into picture. And what will be this distribution then? This is still exponential, that is the beauty of it, and with a parameter which is lambda plus mu. That is the beauty of this whole things. So, every time whatever happens, we see that it is all exponential. Next event is again exponentially distributed, that means all the event separations are actually memoryless. Therefore, from the observer's point of view, it does not matter where I start counting, I can still say the rest of the things are all exponentially distributed, whatever happens. So, that is the beauty of this queuing. It is a very fundamentally different things from all other things that we know. So, that is why it can be actually described with number of customers they are there, because at any point of time if you go in, you will be able to see how many customers are there inside. So, over here as you can see, at this point if you try to target, so basically there was 0 customer over here, from here to here it is actually having 1 customer in the system, from here to here it is having 2 customer in the system, from here to here, okay. So, it is actually having 3 customer in the system. There one departure happens, so it again comes down to 2, here it comes down to 1 and here it comes down to 0 and again this is 1. So, this evolution of number of customers are happening because intermediate part whatever is remaining, that is still exponential with the same parameter. Therefore, I do not have to characterize how much time has been elapsed, how much time is left. So, those things are not required. Every time just this number I can keep on recording, and the next thing that will be happening, because of this exponential memoryless property, it will be only dependent on the current number and not previously what has happened. So, all those history is not required. I can summarize the whole thing just with respect to these state variables, single state variable. That is just the count, number of customers that is inside, okay, who are still waiting for their service. They might be waiting over here taking already the service, or they might be waiting over here to their term to come. Whatever happens, I do not discriminate also among those customers or among those packets if they are packet. I just count the overall number and I comment on that. This is the beauty that will be happening as long as I take this exponential distribution for arrival and for service. Okay. These both the things, if they are exponential, then we have understood, because of this nice property of exponential distribution, that minima of exponential is exponential, exponential has a memorylessness property. So, therefore, from any point of time you cut the exponential and then rest of the things is still exponential distributed with the same parameter. So, basically I have all this information and I do not need any other things to describe this system. There is a whole interesting aspect of queuing analysis or Markovian analysis that we will learn later on. Okay. So, I hope this is clear to everybody. So, with this I can actually probably go towards the first part of our, so far we are just discussing generic aspects of distribution, how they are interacting with queuing systems and all those things. Now, we can go ahead and derive some more things about the actual queuing. So, what we will do, we will, as promised, we will first derive Little's formula. So, what is Little's formula? Let us try to understand this part. This is actually telling that suppose I have a queuing system, okay, followed by a server. It might be single server, it might be multiple server. So, how these servers are serving them, that might be also means you might have some particular way of serving them, that you have a priority and all those things. It's all these things can be there. Even queuing discipline also can be anything. It might be random, it might be LIFO, it might be FIFO, it does not matter. It might be smallest job first, and all kinds of things can be happening over there. So, whatever happens, what I am trying to understand now is, can I get some average relationship between three parameters. One is the arrival rate, the other is, so this is average arrival rate, then the average number of customers or packets or calls in the system. Remember, in the system, whatever we call as system, we will also talk about that. Okay. And the average means overall time spent. In the system by all these customers. Okay. So, can I get a relationship? So, we will represent this, we already this we have characterized, that is lambda. Okay. So, customer in the system will represent as n, and this will be representing as w, waiting time. Okay. So, basically this means actually the customer enters over here and whenever he departs, it is the time between these two. Okay, the gap between these two, that is the overall system time that he requires to get service. So, if I just see in my these things, so for the first customer, this is actually the overall system time. For the second customer, this is the overall system time. For the third customer, this is actually from here, this is his arrival, this is his departure. So, that is the overall system time. For the fourth customer, this is the overall system time. So, like that if I do bookkeeping I will get all this system time and then I can take an average over a very long duration. So, I can observe this whole thing for a very long duration and I can take average over them. So, once I take those average I will be able to means get that value of waiting time. Again number of customers. So, basically you have seen for this over here it was 0, for this amount of duration it was 1, we have already recorded that, for over this duration it was 2, this was 3, this was again 2, this was 1, 0. So, like this we can take and do a time average, that what is the average means what is the average number of time, average amount of time over the whole observation period for a very long observation, that I have seen him in state 1, state 0 and all those things, and I take the means I take associated probability and then I take the average value of that. So, I get the average n, these things. So, average number of customers generally in the system, present in the system. So, this is not instantaneous, it is the average taken over the whole duration. Without doing any queuing analysis, can I give a relationship between these two? It turns out, and which was proven by Littles, that this is achievable, this can be done. So, let us now try to see how do we derive it without doing any queuing. Okay. So, no queuing analysis, no means whatever be the arrival rate, that might be exponential, that might be other things also, means inter-arrival might be exponential, inter-arrival might be any other distribution, service also might be any other distribution. So, we are not restricting ourselves right now. Okay. When we started restricting ourselves, but right now we are not restricting ourselves, we are trying to derive an average formula. So, we are not going to discuss about the whole statistics, just an average formula which will tell us the relationship, interrelationship between these average quantities. This is a very strong tool, because if one of them, this will be generally given, if one of them you derive, the next other one you do not have to derive, that is the beauty of it. So, basically statistically you derive the whole thing and then you take the average, this is generally what we do, right. But over here what we are trying to do is we will try to develop a relationship between them, so that one of them I derive, the other one is already means readily available because of this formula. And this is a strong formula because it is true for any distribution of arrival and service process, okay, and any irrespective of any queuing discipline that we will be putting over here, or any kind of number of servers you put, all those things, how the servers are serving. So, all those protocols that you will be implementing inside, it is not dependent on that. That is the beauty of this formula, and you will see when we will be deriving, it is really not taking any such things into account. So, in this class what I will give, I will first give the sketch of this derivation, and next class I will actually solve this one. So, again we will actually, just to help yourself, we will do a bookkeeping again, event bookkeeping I call it. So, in time you are just trying to see, but over here we will actually draw, instead of just event bookkeeping, we will do little bit more informative event bookkeeping actually. We will also count the event that are happening. Okay. So, over here I will be putting the count over time, and this is the time. So, as time evolve we will keep that count. So, basically what do I count? So, this particular things from the system perspective, there are only two things, one is the arrival which is the event, and other one is the departure. So, these are the only two things I will be counting over here. So, let us say from time t equal to 0 I start, at this point one arrival happens. So, immediately this is the count. So, basically the arrival count will go up. So, it will go up by 1. So, this is an integer, this one 1, 2, 3 and so on I am doing. So, this one will go up. Now, this is where C1 happens, this is where probably C2, the next arrival happens. Immediately the count, overall arrival count I am just counting, right. So, the count will go to 2, this is where probably the third one happens. So, the count will go to 3 and so on, it just goes on like this wherever it goes, and this will be, as you can see, it will be means monotonically increasing, because the count will only increase. If nothing is happening for a longer duration, it will be flat. Whenever another arrival happens, immediately it will jump. So, it is such a monotonically increasing staircase kind of thing which goes to infinity, right. So, it just keeps on increasing. So, this is, we call it the arrival curve or arrival count curve over time. Okay. Similarly, what we will also do, we will count the departure. So, C1 comes over here, probably let us say C1 departs somewhere here. So, then whenever it departs, the other counter from here, it will just keep counting that and it will increase the counter. So, that is the first departure which has happened. Let us say that is the next departure, this is the next departure. Okay. This is the next departure. Now, let us try to understand. So, this is, I call it, this is arrival, this is delta t. So, departure count. Can I say anything about these two, this alpha t and delta t? What is the relationship? As we have seen, alpha t and delta t can touch each other, that is possible. This is where it has happened. That means, as many, the count is same, that means as many has arrived, that many has depart. What does that means? So, at this instance basically there is nobody in the system, everybody who has arrived, they have finished their service and they have departed and no fresh arrival has happened. So, system is going empty, that means nobody is there in the system. Can this be happening that the delta t curves actually overpowers or it goes beyond alpha t? That can never happen. Always delta t must be less than alpha t. This is because as many, this is a count, right. If the arrival count, can the arrival count be less than departure count? That cannot be. As many customers has come, only they can depart. So, there cannot be new things which will be generated from the system who will be departing, it cannot happen. So, therefore, this delta t can never go and surpass alpha t, this will never happen. Occasionally, they can actually close down their this one. Okay. Now, some more observation over here. What is this thing? The height of this one, that is actually exactly tells how many are there in the system, that is over time n how it is evolving. Can you see this? Because at this instant this difference says it is equal to alpha t minus delta t. What is that actually? As many has arrived minus as many has departed, rest of the things will be there in the system. So, that is actually, I can call that as n t, over time how many are there in the system. So, every time instant it will give the count, good. So, this graph is very useful. What does this gives me? This actually tells me this is the first arrival and the corresponding first departure. This is the second arrival and this is the instance of second departure. So, this is actually waiting time of, let us say, the nth customer. This exactly gives me the waiting time of the nth customer. So, therefore, horizontally and vertically we can actually make some sense out of it. In the next class, what we will try to do, we will try to take these things into account and try to derive the relationship among themselves. We will try to see that, appreciate that in the next class. Thank you.